Yeah, so the topic this evening is water supplies. The objective of this show is to provide an overview of water supplies in New Zealand, provide knowledge relating to installing, securing and maintaining water supply pipework in buildings. It's fairly broad. Could do a bit of general stuff on where the water comes from, some specific stuff about pipe systems. Throughout that, try to hit a few markers with the questions that you're being asked as well. So it does cover quite a range of topics. Conclusion of this one, this is the long slideshow. I'm going to have a brief slideshow on materials used in water pipe systems, which is its own standalone unit standard. Reference documents. New Zealand Building Code G12 is one of the key ones here. AS NZS 3500 Part 1 Water Services is an alternative standard for water supply design. Covers things beyond the scope of G12 like commercial installations. It has a sizing section. It's Appendix C and D off the top of my head, where you can actually size for a domestic house, or you can actually size development with multiple tenancies. We're not going to cover that in detail, but there are a couple of questions loosely alluding to it in your assessment. Your study guide. The study guides, I've had a look at those. They're actually reasonably good for these topics, cover most of the information in a reasonable level of detail. And one funny thing I did find in there is a picture next to someone doing a crocs nut, which is me. If you click on the PDF version, it takes you to my YouTube video of me showing how to do it. So Skills haven't paid me anything for that, but I won't hold it against them at this point. To access standards, we spoke about this the other day. You can access Standards New Zealand via your PGDB login. New Zealand Building Code documents are free. You can actually just Google NZBC G12, for example, and that should be the top of your search thing. But they are on the Department of Building and Housing's website. Right, water supply. So I'm just going to use Wellington region as an example. So the Greater Wellington region water supply uses approximately 120 million to 220 million litres per day. So it's a pretty substantial volume of water being consumed by domestic housing industry and that sort of thing. There's three main areas where that water comes from. There's the Timarua catchment area, or Timarua treatment plant, which catchment area is the Taitoki River, and there's the Wainui treatment plant, which catches from Wainuiomata itself and the Orongoronga Valley. So there's actually a tunnel through there, taking water to the treatment plant. So a tunnel, Kaitoki, taking water through the hill to the treatment plant as well. So they do a range of treatments there. They screen it initially. They add aluminium sulfate to clump together all sort of floating particles. That comes off as a scum in a sludge layer, so it gets separated. Then it goes through massive big sand filters, and then it's treated. So they add chlorine, they add fluoride. Chlorine's to kill bugs and bacteria that are in the water, and the fluoride's to make people's teeth stay strong. They do a lot of testing, so they test the chlorine levels, which you don't want too much. That can have negative effects, affecting brass and copper. If you don't have enough, then you may have bugs developing in your network as well. So they monitor it. They monitor it even way over in Miramar to see if there's a residual amount of chlorine still in the water. If there's no chlorine left when they sample it over there, it means that it's run out, it's used it all, and there was actually nothing potentially protecting future bugs from then growing within the network. So it's an ongoing thing. They're always altering it. The water coming into the treatment plant's always slightly different. You have a flood. You think you have a flood, great, there's loads of water. Well, they can't actually always take water at a flood because there's too much debris. There's too many solid particles in there. It takes too much treatment to get it to a standard that's suitable. No one really wants brown water coming out of their tap. So they're limited in what they can do. Same time, in the middle of the summer, when there's a drought, they can only take they've only got resource consent to take so much water out. They can't drop the water level too low in the river. That can be an issue as well. So it's a bit of a balancing act, which is why it is important that plumbers, are aware of water restrictions, promote other means of recycling water or use of water through rainwater catchment where practicable. And it's definitely going to be a bigger thing moving forward. Some areas, Kapiti, it's a requirement to have a rainwater tank, basically to prop up the supply and reduce the load on the network, which is cost saving as well. The other big source of water in our region is the Waifatu aquifer. So there's at Waterloo, there's a big pump station and it draws water out of a bore from the aquifer. Now, the water itself basically sinks in from the Hutt River round about the Pulmari train bridge, and it travels through a whole heap of gravel layers and effectively gets stuck in a layer between impenetrable rock and seabed and the land above it. So underneath most of the Hutt Valley, it's actually full water. It naturally sort of leaks out into the sea in the harbour. If they pump too much out, they pump out a huge amount of water out of there, but if they pump too much, they could get saltwater ingress, which could contaminate the whole aquifer. So they have to monitor that as well and make sure they don't get too greedy with it and make the ground unstable and or contaminate the aquifer. Potable water is the term you need to be familiar with. So it's basically water that's safe to drink. Water supplied from town supplies is required to be potable. There's drinking water standards that regional councils have to abide by. But sometimes it does go wrong. Havelock North was one example where they had a contaminated bore. They didn't realise it quick enough, and about half the town got poisoned. And there were some pretty severe reactions. A couple of people died, older people, rest homes, things like that, that didn't have a robust health. The effect of getting might have been Campylobacter, one of those waterborne diseases from that contaminated water actually was enough to kill them through dehydration, vomiting, that sort of thing. So what is potable water? It's clear, pleasant to taste, odorless, dissolves soap easily, so it's not hard water. No organic matter, or very little. No organisms that may cause disease. So sort of chuck this one in here. There's a few questions in your assessment and it directs you, but you're going to have to be directing yourself back to G12 to answer them. So you need to work with G12 as you go through and look at this assessment. So a couple of things that are topical on water supplies is buildings provided with water outlets, sanitary fixtures, sanitary appliances must have safe and adequate water supplies. That's a functional requirement of G12. Paul touched on what they are, the functional requirements, the objectives of building code documents yesterday. So go in there, have a look right at the beginning. you'll find those key points. But the big picture things you must comply with. Another clause I've pulled out relating to water supplies is protection of potable water. Water drawn from the water main should be prevented from returning to that system by avoiding cross connections and backflow. So plumb is critical here in protecting the potable main. If we do our job incorrectly, if we create a potential cross connection with an unsafe supply of water in a property, we may not only poison the people that live there, we could potentially poison the whole town. So that's one of the reasons why plumbing's a registered trade, and it's limited on who can do that work. Because if any Joe Blow could crimp a pipe, it could be a plumber, it would be a free-for-all, and there'd be a lot more poisoning situations. There'd be a lot more negative health outcomes from an unregulated industry. So we need to take care that what we're doing is done correctly, it's done compliantly, and it's done safely. So we're protecting ourselves and our customers and the general public as well. Waterborne diseases. There's a whole range of waterborne diseases that can be transmitted through water. Water's quite an amazing thing. It's critical to life on Earth. We can't survive without it. Lots of things become soluble in water, so they dilute in water, and you can't even see them anymore. They're just in there, invisibly, basically traveling around. And some of those things can be quite nasty, particularly when the quantities get up to a dangerous level. So there's a range of things: E. coli bacteria from feces, dead animals, things like that, Legionella bacteria, and small quantities that's in there even after the treatment process. Salmonella, Cryptosporidium giardia. I've seen ads in the past on TV saying don't, randomly start drinking water out of creeks, and that's because that water, even though it might be in the bush, lovely setting, you think there was no pollution up here, well, there might be a dead possum up there. There might be something in the ground. Legionella bacteria just live in the ground, in the earth of the ground anyway. So you might be drinking water that's contaminated. And if you're unlucky, that's going to give you some severe reactions, vomiting, diarrhea, in a short space of time. And if you're too far from medical care, you could have a bad outcome. You might not be able to get back out to civilization. So we need to protect our water supplies from these things. When that breaks down, when you don't have robust plumbing and water that is actually treated correctly to a reasonable standard, people die, and that's happening all around the world every day. So there's lots of countries where they don't have a robust, safe network. You can't drink the water that comes out of the tap. And if you do, you're likely to have some really negative health effects. Obviously, places where they've had a war, people are displaced, they all end up congregating in a refugee camp somewhere, and it doesn't take very long before the lack of sanitation pollutes the water supply, and then suddenly people start dying very rapidly. All right, moving on from those negative thoughts to more positive stuff. Start of the water supply. In New Zealand, the water supply and the Toby are owned by the council, and that is effectively the start of your water supply. That's going to be at the property boundary. Multi-unit tenancies, like apartments and things like that, it's a requirement. There's an isolation valve for every tenancy, not just one for the whole block of 50 units. That would be a plumbing nightmare if you had to go and change some tap washers or replace a hot water cylinder there, and you had 50 other people moaning at you all day long. So it is a requirement in G12 that they can be individually isolated. Pipe materials. must be suitable and not contaminate the potable water. So they must be constructed to recognise standards. Now, G12 lists a range of materials, these ones here: polybutylene, copper, galvanised steel, and for cold only, PVC and polyethylene. Other systems which are becoming more popular, like PEX pipe, crimped stainless steel. So there's plenty of other things out there. They're effectively a proprietary system. They would still be installed or made to a recognised standard. But the installation requirements won't be covered by G12. Won't tell you clipping distances for a system that's not listed in G12. You have to go to the manufacturer's instructions, or possibly an installation standard for that product. Pipe joining. Your plumbers, you should know how to do this. There's a couple of questions on that, but obviously copper, brazing, crocks joints, PVC, solvent cement, PEX, polybutylene, crimped. There's a couple of questions on this. They're semi-multi-choice. They can be a little tricky. There is a funny one there. I took a note and I didn't put it in front of me because I was just in another meeting. But there's a funny one there about a flexible flexi going on to brass. Now, personally, I would think it's compression, because the thread, you've got a male thread coming out the wall usually of the brass, and then you've got a female thread on the flexi, and you tighten them up and it compresses the washer and seals it. Well, they've got it as a threaded connection, I think, which to my mind is a male-female thread with thread tape. So that's an interpretation thing. So watch out for that one. If you get it wrong, you should be able to have another crack at it next time around. Let's check your first answer. Funny one there. I took a note and I didn't put it in front of me because I was just in another meeting. But there's a funny one there about a flexible flexi going on to brass. Now, personally, I would think it's compression, because the thread, you've got a male thread coming out the wall usually of the brass, and then you've got a female thread on the flexi, and you tighten them up and it compresses the washer and seals it. Well, they've got it as a threaded connection, I think, which to my mind is a male-female thread with thread tape. So that's an interpretation thing. So watch out for that one. If you get it wrong, you should be able to have another crack at it next time around. Let's check your first answer. Pipe sizing. I'm not going to go through how to do this in any level of detail. We may touch on it in a future bot course if we get the chance. We used to do it in the old system, so we do have some resources on it. If you do want something, practice activity on it, you can always hit me up via email. But in AS 3500 Part 1, Appendix C has got a worked process for doing it for multi-buildings, multi-tenancies. And then D has got domestic one. It's similar to gas pipe sizing in terms of process. It's probably a little bit more confusing because you've got to jump from the back, the appendix at the back, right to a section at the front, then to another page a bit further on, and then put that information into a table, come back and work out your sizing. If you do the gas pipe sizing, you can definitely do the water pipe sizing. So when you get to module 7, 6 or 7 and 10, you'll be doing the gas pipe sizing. So there'll be some transfer of knowledge there at the very least. If you're interested, you can go and have a look. Material selection considerations. So there's some things to think about. Most plastic pipe work needs to be protected from UV light. Under UV light, it will break down over time and it will fail prematurely. That won't happen in one day, 1 week, 1 year. We're talking multiple years. But it's going to shorten the lifespan of that product, and it will cause it to fail. So as part of being a competent tradesman, you need to be aware of that, and you need to protect it from that UV light. That may just be insulating it, maybe painting it, maybe wrapping it in tape, maybe relocating it to somewhere more suitable. Same applies for PEX, gas PEX pipe. Same thing, it's got to be protected from UV light. Different materials and fittings provide different flow rates. So if you're bending a swept copper bend, that's going to have substantially better flow rate than a crimped polybutylene fitting, which is square at 90 degrees. And that can be an issue when you're upgrading an older bathroom, which was in copper, and then you're redoing it, you're changing it round, you're putting a new mixer in, that sort of stuff. Everything originally was set up for low pressure. If you're not upgrading the hot water cylinder, and you suddenly expect the old system to work with reduced all these extra friction, you can have some negative outcomes, and basically you can get a system that doesn't deliver what the customer's expecting. And once it's all finished, it's very hard to go back and rectify that. So definitely you need to try and minimize the amount of fittings, or make sure that you've got adequate pressure to compensate for the flow loss you're going to experience. Expansion allowance. Different pipe materials will expand at different rates. The type of expansion we're most concerned about is lineal expansion. So lengthwise. If you've got a pipe going between two fixed points, like going through a concrete floor, if its expansion is too great, it could shear that pipe off, might break it, causing it to fail, might cause it to deform and de-shape, and snake all over the place as well. So we need to make some allowance for expansion, and high expansion systems will need, it's a bigger consideration. Fusiotherm's one example. All the design of their clipping and where the clips go is really about focused on managing the expansion that the system can come across. So they have fixed clamps, and then they have sliding clamps, and you've got to position them in the right place to compensate for the expansion that that system will experience. If you don't do it right, you potentially void the warranty that they offer, and the system may fail. Temperature ratings of systems, like we saw initially, PVC and polyethylene aren't rated for hot water. So not every system can do everything. So I'm just going to shut my door so my wife's noise isn't so noisy. I'm not sure if you could hear the background noise, but I couldn't. It was a bit distracting. So a few other things. There's a New Zealand Building Code B2 that lists minimum periods, minimum guarantees that products are required to last. It's relatively simple. You can go in it, list some specific things and how long they are, but there's basically 3 requirements. If you can never get to it again, for example, it's under a concrete slab, it's required to last 50 years. If it's difficult to access, for example, behind a jib wall, pipework in the wall, it's required to last at least 15 years. If it's exposed, it's only required to last 5 years. So if you just think of the scenario, apply those 5, 15 or 50 to that, you'll be able to work out questions relating to B2. Some environments may aggressively corrode metal pipework, so areas close to the sea, pipework run underneath wharf, for example. Saltwater environments are going to hasten the corrosion of metal pipework. So if there's an alternative, plastic pipework in those situations might be the preference, because they're not going to have the same effects. They're not going to rust. Even copper can corrode, won't rust, but it can corrode in harsher environments. Pressure rating of the system, and when frost protection is required. So metal pipes are very rigid. They don't like freezing. They tend to fail. Plastic pipes have got a little bit more expansion in them. But again, if they do freeze, there's the potential for them to fail as well. So typically anything outside the thermal envelope of the building will require insulation to protect it. It's just a chart showing the difference in lineal expansion between some different materials. So you can see steel is relatively low, aluminium slightly more, copper considerably more than steel, but nowhere near as much expansion as polyethylene. It's just really to give you an idea of the differences. So plastics tend to have much higher expansion than metals, for example. Holes and notches. There's a whole detailed section on here about how big the holes can be. It's not just joists, it's also through studs, top plates, going through studs, going through bottom plates. So there's maximum sizes you're allowed depending on the size of the timber element. And there's also minimum distances between holes. There's a whole big range of requirements there. This assessment doesn't get too detailed on those, but does have a couple of, at least one question relating to it. So the main reference document for that is New Zealand Standard 3604, which is the standard for building timber frame buildings. A lot of that information is also relevant to penetrations, is also replicated in AS/NZS 5601, the gas standard, and also AS/NZS 3500 part 1. But 3604 is the head and the main standard. If you don't have access to that, you could probably find enough relevant information in the other documents. Just one thing on that. If you are required to do a bigger hole than what's allowed, they do now make stud stiffeners or top plate stiffeners. So there are alternatives to get you out of a jam. So for example, a 50mm pipe in a 95mm wall, you're not allowed to do that. But with the additional installation of a stud stiffener, it then becomes compliant. So there are ways and means to get the job done. It just requires some knowledge and an additional product to be installed. Working safely with these pipe systems, a couple of things here. We touched on an earlier slide the other day, using a bonding strap when you're cutting metal pipes. What you might not be aware of is that when you've got metal pipes and metal fixtures in a plumbing system, they're actually required to be earth bonded together. It's called equipped potential bonding. And the requirements of that are spelled out in G12. Now, you might think because it's wires, it's a Sparky's job, but it's actually part of the plumbing requirements. If you don't have the right gear, you can always get your Sparky mate to do that, as long as you're overseeing that it's done correctly to comply with G12. Couple of other things on there. I think I go into Hotworks in a minute, so we can go past that. There we go. So other things, depending on the product you're working with, if you're doing brazing, for example, with copper, there's a few other considerations from a safety perspective, which is one of the reasons why it's become less popular. Also the cost of copper, the cost of materials compared to plastic and the installation time tends to be about double. So things are not working in copper's favour. But if you are working with it, there's still applications where it's relevant, or people just want the best of the best, something that's proven. Then it's important to have a safe work process in place. On a commercial site, you will be required to fill in and complete a hot works permit outlining what work's going to take place, how it's going to take place, how you're going to keep the work area safe. And that's just part of the job. It's part of the new world. If you don't do those things, you can find yourself, or your business, the company, can find themselves in a bit of hot water in a difficult situation. There was this example taken from the board's info brief, where a particular company, one of the, he wasn't quite an apprentice, but he just sort of finished his apprenticeship, wasn't actually qualified at the time. That was a sort of separate issue, but he'd gone and done some, he was doing some work on a copper water main on a house, and went in there, got his gas set out, rushed into it, busy working away, and caught the building paper on fire, and ultimately ended up burning the house down. And because he hadn't put these protective measures in place, he couldn't put the fire out, he couldn't prevent it, and the insurance company didn't want to pay out. So it was quite a big issue. I think they may have come to some agreement in the end, but it was obviously very stressful for all involved, and he no longer works for that company either. I was intending to give you a few more opportunities to chat and discuss things, but I'm working up to it. Hang in there. Pressure testing. So once you've installed all your wonderful pipework, whatever your system is, you need to ideally pre-flush it, get any rubbish and debris out that might have got stuck in there when you were doing it, dirt in the pipe, you're crawling under the house, whatever it is, clean it out. And then you're going to set it up on test. So before you do that, you need to isolate any tap shower mixers, things like that, that aren't rated for test pressure. So most shower mixers aren't rated for 1500 kPa, which means if you pump them up to 1500 kPa, they'll potentially fail. If they fail because you've mistreated them, you may not get a warranty claim, which means you're paying to replace them. G12 requires you to pressure test an installation at 1500 kPa, which is just over 200 psi if you're American, for not less than 15 minutes, and then go around and inspect the system for leaks. AS3500 Part 1, for some reason, requires you to test at 1500 kPa for 30 minutes. That's what it says. In reality, usually you pressure test it and leave it on test till the inspector turns up, and that might be a day later, you know. So generally 1500 kPa is approximately about 3 times the normal working pressure. Usually on a new build, you'd put a limiting valve on and limit the pressure in the pipe work to about 500 kPa. In terms of supply pressure, depends where you are. Probably the most you'll get in the Wellington region is about 1200 kPa. If you live at the top of a hill, you might only have a couple of hundred kPa to work with. If that was the case, you might need to actually upsize all your pipes to make sure you're getting the adequate flow rates in your fixtures. Commissioning. Quite often people mix up testing and commissioning. They're not actually the same thing. Testing is testing. Commissioning is checking that system before you hand it over to the customer at the end. So you think, okay, you test it, that's like your pre-line inspection. You might go away for 2 months. Someone jibs it, you know, they paint and plaster it and tile all the walls. Then you come back, you fit all your fixtures. Then right at the end, you're doing your commissioning. You've done all the job at this point. So again, you're doing a visual check, checking for leaks, checking all the valves are open or closed as appropriate, checking systems, the water level in the systems is okay, they're not overflowing. everything's good there. You're checking you've got the right valves installed, or they're set at the correct pressures. They're not discharging. Stored water temperature. If you've installed a hot water cylinder, you need to make sure that it's actually above 60 degrees in the cylinder. Otherwise, you won't kill the Legionella bacteria. Hot water delivery temperature. So it's likely that your hot water cylinder is going to have a tempering valve. In a normal domestic house, you've got to temper that water down to no more than 55 degrees. So you can't have it above 55. So you need to check that that's set correctly. If you're in an old folks' home, you'd have to turn it down to 45 degrees. You've got to check that you've got adequate flow rates at your fixtures. Maybe when you've got multiple fixtures going. If you did a sports ground or something, there's no good having 10 showers if you can only have one shower going at once, because your pipe's all off a 15mm pipe. They want them all to work. There's actually minimum flow rate requirements in G12 that you're required to meet. So potentially an inspector doing his final inspection could check to make sure if you turn the tap on and stuff all came out, he could test that flow rate, and if it didn't meet the minimum requirement, you as the plumber's got to find a solution, which could be very difficult after the job's all finished. Check for noise, water hammer issues. Maybe you missed that clip. It was difficult to reach. You're going to have to find a solution to that problem. Pump operation. Not every house is off the town supply. There's plenty of other water supplies. If you're rural, you're likely to get off your roof or a well, bore. So there's a whole other range of plumbing out there for off-the-grid properties. I got those last two. Now in the assessment, after all that, it starts to ask you a few questions where you've got to use a bit of problem solving. And as Mr. Spock says, it's all about the logic. You need to use your logic to identify what the problem is. Now, you can't do that if you've got no understanding of how the system works. So let's have a think about it. I'm going to be checking the chat now. So here's your first question. Poor water flow. So you've got a system, they've got poor water flow, but when you check it, you've got a high static pressure. What could be a cause? Think about that and type in an answer. So you know you've got pressure, but you're not getting much water out. What could be your issue? So it's obviously not your static pressure. Your static pressure is fine. You might have 500 kPa. Is there anyone out there? There we go. Yep, undersized pump drawing from a tank. It's a good example. So you might have a pump that can produce a certain amount of head, certain amount of pressure, but it might not deliver enough volume for what you're trying to, for the size of your outlet. That's a good one. What about on a mains pressure system, on a town supplied system? Can someone else think of a situation where you might have poor water flow? It might not be every outlet. It might just be one particular outlet. It might be two outlets. Has anyone encountered this problem? Yep. So we get a few answers here. Block filters. Yep, that's definitely a possibility. You can get that on a pump system as well, but some people have filters, even just line strainers. So if they're blocked up with a stone, I've had that before, line strainer blocked with a stone, and the symptom was that they had a crappy shower, or the shower would go and then it wouldn't work properly. So initially they didn't even tell me that you know, it was affecting all the outlets of the tap. It was only once I got there, started mucking around with the shower, I think it's a shower mixer issue, that I got out of them, that it actually happened at other outlets, and eventually traced it back to a rock in the line strainer that happened to be in the ceiling of the garage, of all places. Another one from Noah, pipes too small, causing less flow. Yep, so if your whole house is piped out in 15 mil and you've got quite a high draw-off demand, you're going to have quite a lot of flow restriction. Also, if you've got a whole heap of bends, you got, you know, an uneconomical pipe run, you've got a whole heap of bends or other things restricting flow. Yep, so undersized pipework. Yep, so there's some reasonable answers there. But yeah, anything in the pipeline is a restriction. The length of the pipeline is the restriction. The further the run, the more friction it's got to overcome to get from one end to the other. The pipe wall itself creates friction. Even a very smooth bore pipe wall is creating friction as the water tries to get from one point to another. That's going to slow down it's going to reduce your flow rate. Won't change your static pressure. Your static pressure will be the same everywhere in that system, but you'll get a lot more water out at the start end than you will 100 meters further down. Why do you think G12 has minimum flow rates? So I'm telling you, G12 has minimum flow rates. Why do you think it would do that? Why do you think that's a requirement? No, it takes you guys a little while to warm up with your typing here, so I'm hoping something's going to come through in a second. Have a stab in the dark. There's no wrong answers at this point. Little off track there, Noah, but thanks for putting something up. No, so the flow won't affect the pressure of the system. So if a fitting was to burst, that would be because the pressure exceeds the rating of the fitting. So minimum flow rates is how much water comes out effectively litres per minute. So if you took a bucket and stuck it under your tap and timed it, you could work out the flow rate. Flow rates are given in litres a second in G12, but you could also convert it to litres per minute by multiplying it by 60. And different fixtures may require different flow rates. So, for example, a hose tap might have a different flow rate than a shower or a toilet. David's put something up, just in case backflow might be needed to be installed in the line. So that's quite what we're looking for. A backflow device like a double check valve or an RPZ will reduce the flow rate. There's a pressure drop across the valve, which is going to impact how much water flows from one side of it to the other. So there are a restriction in flow. It's probably a slightly funny question. So G12 is going to have minimum flow rates because, you know, the big picture requirements is that you have a functional system that's suitable for purpose. So you're providing people with water for sanitary reasons, hot and cold water, so they can wash, keep themselves clean. And if it doesn't come out of the tap at a reasonable rate, they can't actually do that. You know, no good standing under a shower and it just drips on you. You can't get clean. You know, you'd be there all week trying to wash with a damp flannel and you can't actually rinse off. So it's got minimum flow rates to ensure you've got a functional system, and that depending on the fixture or appliance that's connected to it, that it's got enough water for that to work at a suitable level. Yeah. So have a look at that. What you could do post this is have a look on G12 and find out what the minimum flow rates are, because I bet you don't know at this point. Boom. Well, here we go. I've got a whole heap more questions. Quick test. These should be reasonably easy because most of them were in the PowerPoint up till now. So here we go. Where is the start of the water service? Where would you find that? I.e. the Toby. Where would you locate a Toby? Prefer Ian's answer there. It may be on the driveway, could be. It's not necessarily. Maybe near the footpath, possibly in it. Technically, it should be on the property boundary. Yeah. So on the street is technically, it's probably not going to get you the mark in the test. So you need to go with the property boundary, inside the property, basically on the boundary of the property. Sometimes it might, like my one, it's 200 mil in front of my fence, so it's probably just outside my boundary, but it's ballpark on the boundary. And obviously you're going around doing plumbing. At some point, if you're doing maintenance, you're going to need to find the Toby. So you'll know from experience where Tobies are located. The white line on the curb, if you can find one of those, should direct you to the line of where the Toby is. Sometimes they are in the footpath. Usually they're just off the footpath, usually just in front of the person's fence. So probably on the street side of the property boundary. For your assessment, go with on the property boundary. Name 2 pipe materials that must be protected from UV light. To make it tougher, you're going to have to name the material, not the brand name of the product. So I want the actual material, the correct name of that material. You don't have to spell it perfectly, as long as I can make sense of it. Yep. So Scott's chucked up what he means is polybutylene. Yep. Using a bit of plumbing slang there. Need to be a little bit more specific, David, because there's lots of different pipe that can be used as gas pipe. PVC, yeah, there is UV stabilized PVC, so which is like used for spouting. So some PVC is actually okay. Not sure. To be honest, I don't know about the PVC used for water pipe. It's PVCU, so it may actually be okay. But that might just be unplasticized polyvinyl chloride, so I'm not sure, but potentially. So we've got a couple of others: alkathene, poly, and Kembla gas pipe. So polybutylene, Kembla gas pipe. That's a brand name, so you haven't actually given me the type. PEX, yeah, PEX is cross-linked polyethylene. PEX for short, what most people know it as. Polyethylene. Dux, yeah, well, again, that's a brand name. So Dux pipe is actually polybutylene. So that may not, technically that wouldn't be the correct answer, but it is. I know what you're talking about, and it is the right type of plastic. So pretty much all plastic pipes are potentially needing to be protected from UV light. If you're not sure, go to the manufacturer's website or the supplier and ask them. What temperature must a hot water cylinder be set above to kill Legionella bacteria? Here's an easy one. Oh, we've got two conflicting answers here. Sorry, David, bombed out there. It was right for a different question. So it's got to be, if you're looking at the chat, it's got to be above 60 degrees. So at least 60, usually it'll be set at 65, but minimum 60 once every 24 hours. So thermostat will be set above 60, and you need to check that as part of your commissioning checks. Do metal pipes or plastic pipes have greater lineal expansion? Oh, Scott's onto it. Oh, took his thumbs up away. He's answering two questions in one. I can't keep up with you, Scott. Yep, I think we all got that one right. Well, the 4 people that are rapidly responding to me anyway, they've got it right. So plastic pipe are will have greater expansion in general than metal pipes. Pretty much all of them, I would think. Other than getting wet, what are the other risk is there when cutting through a metal water pipe, and how can you protect yourself? That's what's going to happen. Yep. So the risk is, yep, the risk is electric shock. How could you protect yourself, Scott? Half the answer. It's a double barrel question. You've got to watch out for those in your assessments because they often catch people out. They only half answer the question, even if they know the answer. Thanks, Scott. Yep. Yeah, in terms of cutting it, you want to use a bonding strap, which is effectively a jumper cable, or a copper wire, heavy-duty copper wire with some big clamps on it. That's going to be a better path for the current than through you, which means that's where the electricity will go. It'll take the easiest path. Right, well done. Move on to the next part of this. All right, seem to be learning something. That or you knew it all already. But either way, I'm happy. Water pressure, hydrostatics. Static pressure for us is measured either in meters head or kPa. You can quite easily convert between the two. Ballpark 1 meter head is 10 kPa. If you want to get a bit more technical, it's 9.81 at sea level. Pressure is a force exerted at any point in a body of water by the weight of water above that water. It's directly a result of the force of gravity and acts in all directions simultaneously. The volume of the water will not affect the static pressure. So you could have a 20 mil pipe 5 meters high full of water. It'll give you at the bottom approximately 50 kPa. You could have a 100 mil pipe 3 meters high. There's a lot more water in it, but at the bottom it's only going to have approximately 30 kPa. So the volume, you could have a swimming pool full of water. If it's only 1.5 meters deep, you're only going to get 15 kPa. You've got millions more liters, but they're only producing as much pressure as the head of water above it. So the higher the head, the more pressure, static pressure you'll have. Just because you've got really high static pressure doesn't mean you'll get a wonderful, huge flow rate. There's all those flow restrictions that might impede that. But as a general guide, if you've got good static pressure and your pipe sizing is adequate, you've got no unwanted restrictions in your system, you should get really good flow rates as well. Certainly at least more than adequate. So that was hydrostatics, static pressure, hydrostatics. And another term they like to chuck around is hydraulics, or hydraulic water flow. I always think of hydraulics as hydraulic rams on diggers, but in this case we need to kind of apply it to a water supply system. So basically hydraulics is when you've got water flowing. Oops, my computer has got issues. It's okay. So all the things in the system are actually going to reduce your flow rate and how much water will flow through that system, regardless of the pressure. So things, elbows, length of the pipe run, valves, different pipes are going to have different pipe smoothness of the bore of the pipe. Any unwanted blockages you might have in there, they're certainly going to do it. If someone's stood on a pipe, squashed a pipe, driven over a pipe, all those things can have negative impacts. And it can be difficult to track these problems down because they're not always obvious. Someone might have put polyethylene down under a house and it had a copper water pipe that's shot up and then went somewhere and then they bent it over and you can't even see it, so that would be a difficult problem to resolve. You'd have to work your way back logically, find out, where it's okay, and then try and isolate the source of the problem and then replace it. You might have to bypass that section, damaged section altogether. You might have galv pipe that's corroding internally and it's restricting the bore, but you can't even see it. You don't even know. So you might just have to end up replacing that whole section of pipe with new plastic pipe. And that's where you find the minimum flow rates, table 3 in G12, page 26. If you're taking notes, you could note that down and find your way there easily. The other thing you could do is you could search those documents if you're looking at them electronically. Go Control F and then type in flow rates. It'll take you to every single page that has the term flow rates on it. Just flip through the arrows till you find what you're looking for. Pressure is the amount of force acting on a given area. 1 kPa equals 1 kilonewton of force on 1 square meter. So the weight of water creates a force, presses on an area, creating the water pressure. That pressure pushes the water through the system. Pressure acts in all directions. So it's pushing 90 degrees to the surface of the pipe wall. It's pushing into everything. It's not just pushing at the bottom of the pipe, it's pushing at the top, everywhere. That's how it gets through the whole spaghetti of pipework to come out at the tap eventually. You got to remember, it's all started way back at the water treatment plant, miles away. Even pump systems, the pump's just creating artificial head to create pressure to push the water through that system. Now, here's just a more of a visual picture showing what that means. So 1 meter head equals 9.81 kPa. Gravity accelerates at 9.81 meters a second. So that's why we get 9.81 kPa per meter, because that's what gravity is, effectively. That's the net effect of it. Ballpark, if you don't need to be super accurate, you can estimate, okay, my low pressure hot water cylinder is fed off a header tank that sits in my ceiling, which is maybe 3 meters above the base of the cylinder. So I've got probably 30 kPa at the base of the cylinder. My shower hose is 2 meters above that. I've only got 1 meter of head to my shower hose. I've only got 10 piddly kPa to work with here. That's why I've got a terrible shower. On a mains pressure system, they might have 500 kPa. They've got 50 meters of head. You've got 1 meter of head. That's a radical difference. So on low pressure, the less pressure you've got to work with, the more you've got to be considering your flow restrictions. You may have to go to a bigger pipe. You might have to try and minimize the amount of bends, fittings, valves to compensate for that. If you look in G12, it talks about low pressure hot water systems. If you've got less than a certain amount of head, you're required to have a 25mm feed to your tempering valve. Probably didn't know that. And that's to try and compensate for that lack of pressure by reducing the flow restriction in that situation to give you, hopefully, a workable system at the end. It's never going to be anywhere near as good as a mains pressure system. Another thing that pops up with low pressure systems is hydraulic gradient. We've got a good model similar to this at work that shows it a bit clearer, and you'll do that when you do the low pressure cylinder pipe outs. But basically what happens is your static pressure is this top line here. So if no taps are open, the water level will be the same as the water level in your header tank. Now when you open an outlet, the water level in all these other branches is actually going to drop down. So your hydraulic, the water's flowing through the system, and your actual pressure that you're getting at your outlet is actually going to be a bit less. If you open this lower outlet, potentially you're actually going to starve this outlet here, this shower rows of water completely, which can happen in low pressure systems. So you're busy having a shower, someone turns on the kitchen tap to do the dishes, you're having a cold shower, and obviously you get out in a hurry and start moaning at people. And that's because when they turn their tap off, yep, the pressure recovers and you're having your shower again, but water will take the easiest path out. And that's called the hydraulic gradient. So the hydraulic gradient's basically the reality of how much water is going to flow when it's moving. It's different than your static pressure. Hard and soft water. Hard water leads to a build-up of limescale, which can block plumbing and promote galvanic corrosion. Hard water will not lather soap and can form scum when mixed with shampoos and detergents. This hardness is caused by dissolved salts. The main causes are calcium, magnesium, and bicarbonate. So they're naturally in the ground. Certain rocks have them within them. And as the water travels through the ground, it tends to pick these salts up. They dissolve into the water. If you've ever been into a cave, you might have seen stalactites and stalagmites. Well, that's basically a build-up of lime that started to solidify over time where there was a drip in the cave. Similar thing happens in your water system as they dissolve, they're in solution, and then particularly when you heat that water, they start turning into scale. And that can cause a whole heap of problems for your plumbing system. It tends to insulate hot water cylinder elements, which means they have to work twice as hard to heat the water and eventually fail because they've been working twice as hard as a normal one. They can block up heat exchangers, copper heat exchangers, instantaneous units. So they basically, anything where you heat the water, they can affect it and cause problems. Less of an issue in a cold water situation. There is a solution, but it comes at a cost and some ongoing maintenance. So there's a thing called a water softener, and that can remove those salts. So it uses ion exchange resins, which removes the lime, calcium, etc. So what it does is they actually get attracted to all these little tiny plastic beads. So it goes through, basically it's a big filter system, but they get attracted to it like a magnet. So as the water goes through it, going through this big filter thing, it gets attracted and they cling on to these little plastic beads because they're positively charged to attract to them. Over time, that will clog up effectively and the thing will need to be cleaned. So it does that automatically. It's got a controller. What it does a backwash with a salt saline water solution. They call a brine tank. So that cleans all those mineral deposits off those little beads without losing the beads, and that just dumps to waste. Over time, the salt bucket has to be topped up, so it'll lose some of the salt each time, but most of it goes back in, and they just top it up with water, and it's reused again. So there's some ongoing cost to it. Another thing we're going to be aware of is galvanic corrosion. So this is the electrochemical process in which one metal corrodes preferentially to another when both metals are in contact in the presence of an electrolyte. So water is an electrolyte, puddles, water. So, for example, sometimes this is actually used intentionally to make things last longer. So, a mid-steel hot water cylinder, you've got an enamel-lined mid-steel, which, if just left normally, would rust. So, the enamel protects it's like a paint coating on it. That's your first stage defense. But also inside it, it's got a zinc anode, which looks basically like a shaft of dull grey metal bolted to the top of it. What happens is that zinc actually loses particles which help protect, it's losing electrons which help protect the steel. So it starts to break down, keeping the steel intact. And they use the same thing on ships' hulls. They bolt big zinc blocks to the steel hulls of the ferry, stuff like that, other big metal ships, and that reduces the rate of corrosion on the hull. So you've got two things. You've got the paint protection, and then you've got the sacrificial anode. Now, this can happen in a negative way in a plumbing system as well. So, for example, if you had copper and steel in direct contact, or even brass and steel, the copper and the brass are more noble metals than steel. So the steel will start to react, protecting the copper or protecting the brass. So it will hasten the corrosion of the steel, which isn't ideal. So, for example, you've got an existing galvanized steel water pipework in a house, and where the brass hose tap's joined on, sometimes it will stop working or clog up, and you take the tap off, the tap seems okay, take the tap right out, and you see that there's a whole big pile of corrosion inside the steel fitting. And that's because the contact with the brass has hastened the corrosion of that pipe, and it may even block the water flow. So ideally, we would avoid mixing incompatible metals or metals where galvanic corrosion will take place. In some cases, that's not always possible, but if we can put a barrier between them, we will reduce the effect. So I would say thread tape would be better than putting hemp if you're going between brass and steel. There is a special fitting, although not in common use for that sort of application, that actually insulates between the two different dissimilar metals. It can also be used to break electrical contacts. It's in this next PowerPoint. So there's a scale there. There's some stuff at E2. There's a bit of info there. So zinc will act as an anode. It's very reactive. And the ones down the bottom, stainless steel, copper, brass, bronze, lead, they'll act as the cathode. So they'll stay intact. So if it's higher up the list, it will break down, protecting ones lower on the list. Another thing we need to have a little bit of knowledge of is pH. Pure water is around about 7. It's basically neutral pH. And then you go the low down on the pH scale, you've got acidic water or acid, battery acid, hydrochloric acid, acid rain, even coffee slightly acidic. So if you've got acidic water, it's going to cause accelerated corrosion on metal pipes. At the other end of the scale, you've got some cleaners: drain cleaner, bleach, soapy water, ammonia. That's called alkaline water. And that can have some issues as well. Water high in alkalinity can kill fish, things like that. If you had highly alkaline water discharging into a natural waterway, it may kill off all the aquatic life and damage that. It's also going to affect the bacteria in a septic tank. So if you're on a septic tank supply, you'd have to be careful what cleaners people use. You have to advise them which ones are suitable, which ones are not, because it may kill bacteria. So if people are on non-town supply, bore supply or something, you may need to test the water quality to find out, one, if it's safe for drinking, and also will it affect the pipe system I'm thinking of installing. If it's acidic, it could be corrosive issue, so you might want to go to a plastic pipe that won't be affected. Or if it's hard water, then you've got to look at your hot water system. Do they need a water softener to remove it? Is it at that level? So there's a whole heap of things that aren't always obvious that can impact plumbing systems, and we need to kind of have a little bit of knowledge around that. Right. Woo! It's been a lot of talking. Thankfully, we're at the end of this one. The other one's a bit briefer. So let's have a go at these revision questions. I'll be jumping on the chat again, see where you're at. So the first one, where would you check a home's water supply pressure? So if you're looking at a house, you wanted to find out what pressure, where would be a good idea to check from? It's a bit of a funny one because realistically you could check anywhere and find the pressure, but if there is flow restrictions in the system or issues, what's going to give you a likely indication of where it starts, what you're starting off with. Yep. Hose tap. Yep. So hose tap's an ideal place. I'd probably ideally, close to the inlet, on the, close to where the tobia is coming in, where the water main's coming in, because you've got less restrictions, less potential issues. Like I said, you can get high static pressure and still have a blocked pipe. So it's not going to tell you everything, but it's going to give you an indication of what you're working with. So hose tap, close to where you're going. If you've got a limiting valve on a system or a pressure reducing valve, the hose tap, usually the first hose tap by the garage or close to where the tobia is usually unlimited. So if that's a possible issue, you can tell, because you might test at the shower or something, find you've only got 100 kPa, but you test the hose tap outside and you've got 700 kPa. So you know that the limiting valve is either faulty or needs adjusting. Right, moving on. When would an anchor block be used on a water supply system? This is a question in the assessment, and their wording is a bit misleading, and it's one people regularly get wrong. So the more commonly known term is anchor block, and that's like in a water main, which is actually a separate assessment. It's like a big in the street water main with a specific type of joining method. So you may not be aware of this one. For some reason, they've chucked it into this assessment. Any ideas? Basically, it's just a big block of concrete you pour in place to hold something in position, or hold the pipeline in position. Anyone ever seen one? Nope. Not really, but that's not a bad guess there. So anchor blocks are used if you did subdivisions and you were doing the drainage and or the water supply to a subdivision, then you might have come across one. So some water mains, there's a range of different products they use. Polyethylene's a big one. Some are steel, some are asbestos. There's some fiberglass. There's all sorts of things used in the water main system. It's a bit of a patchwork. Some of it is pressure PVC that relies on a rubber ring joint. Not the same as the drainage one. The ring's much bigger and thicker, but there's internal forces trying to push that system apart all the time. And it's requiring anchor blocks, big concrete blocks, at changes of direction, under fire hydrants, things like that, to hold it all together. It's totally reliant on those anchor blocks from preventing the internal forces when you get to like a change of direction, blowing the thing apart. So that's when it would be used. Obviously, there's a reason why people keep getting it wrong. Maybe something in study guide, I didn't get to that level of detail. Non-potable pipe work should be installed in what colour pipe? So if you were doing non-potable pipe, there's actually a designated colour for that. Thanks, Paul. Yeah, it's effectively purple. Lilac would be okay. I think their model answer says purple. So you can buy, go to the merchants, you might see this pipe in different colours. Yellow's for gas, purple's for non-potable water. The actual colour for a potable supply is forest green with a blue stripe as potable water. But obviously you're putting in whatever product you're putting in, domestic thing, you don't have to identify it. You know, it's whatever colour the pipe is. Could be grey, could be black, could be copper colour if it is copper, could be metal. In a commercial situation, you're required to identify pipelines because otherwise it's just a pipe. There's a whole heap of pipe in a commercial building. If you don't know, if you can't obviously trace where it comes from, it's got to be labelled or colour coded. Why might condensation from a cold form on a cold water pipe? So obviously on a hot pipe, we're trying to keep the heat in for energy efficiency. But why might condensation form on a cold pipe? Yep, so we've got a couple of slightly different answers, but they're both kind of on the right track. So yeah, so a cold water pipe is going to be cold. It's going to be colder than the surrounding air, potentially, especially if water's flowing through it. Kind of similar to your windows almost. Yeah, if you've got single glazing, it's freezing cold outside, maybe 5 degrees in the middle of the night, but you've got a warmer temperature inside. But as that warm air cools, the humidity increases, so it can actually get to saturation point or dew point and form water droplets on the window, which we know as condensation. Same thing can happen on a water pipe. So if you've got lots of hot, moist air in a building, it floats up to where the super cold pipe is. You see it on refrigerant pipes, like commercial chillers and stuff like that. You have to insulate them. If they don't, then it ices up or starts dripping condensation everywhere. So yeah, so that air that's in contact, the moisture content of that reaches 100% humidity, and then it forms water on that surface, which happens to be the pipe. If it's really bad, it'll start dripping down on your head or something, which is a bit unwanted. So to prevent that, you can insulate it, you can lag it, which means there's an air barrier between it that doesn't move anywhere. So the air close to it gets cold, the air on the outside of the lagging is warm, and they're never in direct contact. So that can prevent condensation.